Hello, YouTube viewers. Welcome to my show, Rocket Monday. In today's episode, we're going to talk about green rocket fuels. So let's dive right into it. Now, first thing you have to understand what we are talking about. We are talking about small thrusters. We are not talking about main engines because main engines are more or less clean. Because let's say, for example, space shuttle, the main engine used hydrogen and oxygen, so output was water. So basically, it was clean. But we are talking about small thrusters. So basically, think of big rocket engines as swords and small thruster engines as scalpel. It's precision. So they are generally low power. Now, when I say low power, do understand it's comparatively speaking because the thrusters that are used in basically space shuttle is much more powerful than used in Dragon capsule. So compared to the main rocket, you will always have lower power. Then it must be controllable. Now this is a critical aspect. When you are talking about solid rocket motors, they are very powerful. Like in terms of thrust, they're badass. But in terms of controllability, they are useless because you can't do anything with them. And in terms of liquid fuel, you might say, okay, in that I can control it. Yes, you can, but not too much. In terms of even Falcon 9's basically amazing engines, they also have limit. They cannot throttle from let's say 3% to 100%. They barely have 100% to 70%. That's their throttle range, 30% of throttle range. So you don't have too much control. However, when you are talking about thrusters, you must have control, and I mean everywhere. Like you must have okay, my thrusters can provide 5 newtons to 50 newtons. Like you must have a range. Or in some scenarios where you cannot have range, you will have a arrangement. Basically, you will have three thrusters. So let's say each one is 10 newton. So you're like, oh, you need 10 newton, you will only fire one. You need 20 newton, you will fire two. You will need 30 newtons, you will fire three. So it has to be controllable. Everything about it is designed for control. Now it's also long term. That's why cryogenic fuels cannot be used. You cannot use liquid hydrogen or liquid oxygen. Now there have been some improvement in terms of insulation, in terms of other things surrounding the system, but we're still not in a place where we can say, okay, you're gonna put liquid oxygen and liquid hydrogen here in the tank and it's gonna stay in liquid form for let's say 2 months or 3 months. It does not work that way. So flat out, it has to be something that can be stored for very long term, and bare minimum time is basically when we talking about is we are talking about around 6 months for ISS, and when we are talking about deep space mission, basically you're going to Jupiter or Saturn, you are talking about minimum 10 to 25 years. So it must be long-term storable, and it must be restartable, because liquid engines, while you can have a third-party system where you can ignite it, but this generally must be restartable in a simplicity sense. So generally people use what we classify as hypergolic fuel. You can check my video about that here. Now restartable makes it very more much more elegant. It's not like you fire the main engine, you go where you have to go, and if you missed it, you missed it. This is much more precise, much more controllable. So we are talking about small thrusters. These are the thrusters used for Apollo mission. So then why do we need that if we already have a big giant rocket and it has gimbaling function and it has small basically it has gimbal, it has throttle capability? Why do we need this? Well, precision control, it's the same it comes down to the same factor. Basically, sword versus a scalpel, you need both of them. So in terms of orbital adjustment, you have to know orbits are very finicky. When you are talking about, we understand orbit in terms of we send something, it will remain in the orbit, but the orbits are never circular. They are rarely in exact alignment that you want it. So we always have to correct it just a little bit, nudge it, do this, do that, circularize the orbit. So they are not very friendly things. So we have to have something that can keep nudging it to make sure that it remains as it's supposed to do. Then we are talking about deorbiting burn. Now deorbiting is compulsory when you are talking about low earth orbits, and there is another version of deorbiting where is a graveyard burn. So basically, if you have geostationary, because geostationary has 30,000 kilometer higher, so falling down, you're gonna hit many satellites. That's why people generally do, they add 5 to 6 kilometer delta extra on the satellite, and then they put it into graveyard orbit, which is higher than geostationary. So you sometimes you can do deorbit burn, sometimes you can do graveyard burn. And you also need course correction, because nowadays there is a lot of serious risk about space collisions. Many military satellites have multiple thrusters to make sure they can dodge basically big chunks, at least not small chunks but big chunks. Let's say a spent stage from Saturn era is still floating around. If that comes around, the satellite can dodge it, but again it has to realign itself, otherwise the orbit plane would be completely tilted. So we need it, and you can't deorbit something like SpaceX without having precision thruster, because even if you have, let's say, big rocket engine that can slow down the speed, if you don't align it properly, you could have a scenario where heat shield is not facing the right direction. So this is why it is a compulsory in space organization or any kind of space vehicle. So what is our current issue? We must be doing it, otherwise we won't be talking about it here. Current option is way too expensive, way too dangerous, and these two are intertwined. Right now we mostly utilize hydrazine. Now problem with hydrazine is basically it does work. There is no denying it. That's why we are using it, but it is dangerous beyond belief. Basically it can ignite, it can give you cancer, and it can burn your skin, and it can kill you, and it can do extra other harms. So you have to understand, even though let's say a barrel of hydrazine inherently is not that expensive, but the people needed to handle this thing adds up the cost. So basically per person, let's say instead of having a person that is working on minimum wage, you need a person that is like equipped with this, almost like a space suit. These things are designed with internal air system. Basically they have their own oxygen supply, because breathing it will give you cancer. So these things add up the cost. So you go from, let's say this is $100 a liter to like $50,000 a liter, and this also adds another complexity. Basically let's say a college student built a 6U satellite, basically 10 centimeter by 20 centimeter by 30 centimeter satellite. It has enough space for small thruster, nothing too big, but it has space for small thruster. He may be more than good enough to build it, but he does not get qualification to fuel it with hydrazine. You have to do it in a clean environment, you have to do it within inspection environment. Like it's not like refueling your truck, car or something like that. It's very complex and dangerous, because these things are dangerous on a level that is very hard to convey. It's like if you are pouring the petrol and like petrol, like okay, I will kill you now, okay, I'll give you cancer now. So you have to understand. And if it fails, let's say satellite blows up, then there has to be a special crew assigned. Like in every rocket launch where hydrazine is used, there is a crew on guard. Like if it blows up, they will neutralize it using chemical agents. So you have to understand, this is very problematic. That's why whenever space shuttle landed, nobody was allowed to go near it unless these type of people cleaned the, like basically made it human safe. Otherwise, like you will be dead around it, not inside the shuttle but outside because there would be fumes of this. So this is very problematic. So then we come to our green option, the whole topic of this video. Now you have to understand, whenever somebody is talking about green option, green propellant and all that, they are not talking about exactly this. They are talking about a concept. Now concept is basically it must be safe to handle. It would be like same more or less like petrol and diesel, because hydrazine also has this one issue. Let's say even if you are completely like sealed up, like you have complete good suit, if you open the, let's say, container, it will absorb moisture from the atmosphere and become diluted. So that's also a problem. These things on the other hand must be human safe. Basically you can give it to a child, and of course as long as you don't drink it, you're supposed to be safe. Basically if it falls on your skin, it should not kill you. It, like, you know, it exposes to oxygen in the air, it should not automatically go kaboom. So this is the whole target of it. This is the target. Basically college student can be like, okay, here's, I'm pouring the fuel, nothing fancy about it. That's the end goal. That is what we call green fuel. And byproducts, whatever you get after you burn the engine, must be safe too. It cannot be like, okay, it is safe as long as you don't burn it. Once you burn it, you get cancer. It should be safe to burn also. And controllability aspect. This aspect simply means there are multiple factors that must go on in order to trigger it. You cannot be like, hypergolics are very good, but they are very active agents. Basically you mix them, no matter what the temperature is, no matter what else there is, it detonates. Many monopropellants are almost ready to detonate. You have to be like, okay, you are sure you're gonna launch it, and just fire it. So you want controllability. Basically must be multiple steps to do to ignite it. It cannot be like go boom. You want controllability aspect onto this. So our solution is basically hydro ammonia nitrate. Again, it's a very fancy name, I can't even pronunciate it, and they're very funny chemical formula about it is NH3ONO 3. Yes, it has ONO in its designation, and if you want like absolute atom version would be H4N2O4. So you have to understand, it has a lot of oxygen which are weakly binded, it has a lot of hydrogen which is weakly binded. So little bit of push and voila, you have rocket fuel. However, it is not stable. So whenever somebody is talking about this, and I'm already talking about making it stable, then why the heck people are talking about this? This is basically like RDX. So if you are familiar with explosives, you must understand RDX is the most powerful explosive we have. Like, of course, other provided some other military contract, RDX is general purpose explosive, but it's way too reactive. Basically you drop it, it goes kaboom. So what military does is generally take the RDX, mix it with polymer, and they make it plastic explosive, or C4. That's what it is. Basically 25% polymer mixed into the RDX to make it stable. And RDX, after it becomes C4, it's so stable that you set it on fire, it will not blow up. You have to use blast cord to detonate it, or blast caps. So this is the same. this itself is not very stable. It is stable, otherwise it simply won't exist. It is stable, but it's not very stable. So we add things to it. We add multiple things. Now this is the critical aspect. You must understand there are many companies who are developing this fuel, so they all will say they are using this, but you must understand they are also adding things. Now that adding things adds certain properties. Like for example, there are multiple mix about it. NASA's mixture is called AFM315E. Now this mixture has the benefit that it requires a hot catalyst. They wanted the system in such a way that it has fail-safe controllability aspect. Basically it will decompose once it's exposed to a metal. Basically generally it's supposed to be exposed to either platinum or silver pure. So that's generally how it works, but because of the additive they added to it, it became stable enough in a point where you can be like, okay, it's only gonna detonate if you heat it up. Basically the metal they have, they're supposed to heat it up to 200 degrees Celsius. Now you might be like, isn't that extra step? Yes and no. Now extra step because heating something is very easy. We know how to do it, and you only have to heat it once. Now this also gives you extra fail safe. Let's say you heated the rocket, you fired the engine, and like you got the satellite, then you cut off the system. Electrical system is cut off, but the valve did not close properly. Now over time it will of course leak. Now here's the deal: once the catalyst has cooled down, it will not ignite again. That is why NASA wanted this. So again, Japanese agency, they are going about it a bit different. Their fuel is more focused on something else, and this fuel in principle, that is why we are testing it, in principle also is freeze friendly. Basically you can freeze it. The benefit of that would be basically you don't have to insulate the tank. You will just put heaters. So let's say you are doing very long term mission, you are going to Pluto for 10 years, you can simply have ion engines that is giving you the main thrust, and once you reach there, because ion engine does not have enough thrust, you can thaw the fuel out. It won't be basically expanding and contracting too much to destroy it. So that is also a good thing. That way we can very safely keep this kind of fuel for 25 years. That's their end goal. For 25 years they should keep working. That's the whole point. And because it needs hot catalyst, you don't have the scenario of like oops, like some contamination happens, oops. That oops should not happen. This is the whole idea of green option. People like school students should be able to handle it. Of course you're supposed to still wear a mask so you are not sneezing into it, but you get the point. So because of the importance of this kind of fuel, this kind of magical thing, way too many players are doing it. Like Japan, just in early 2019 they already launched it. There is already in space, it's already doing demonstration. Then you are talking about NASA mission, which soon will be launched using Falcon Heavy. Then you are talking about Rocket Lab, they are also making their own mix, and that has already been launched. So you have to understand everybody is going at it, because this is a next level evolution. Because okay, we can't do much about our main engines because of the how physics works and how specific impulse works. We can't do much with it. Like if somebody says like I can find something that is more energy dense than let's say hydrogen and oxygen mix, either they are lying or they are talking about nuclear. So you have to understand we can't do much. Like you can do methane, but again methane does give you a bit of thrust, but it does compromise your specific impulse. So we reached the point. In terms of main rocket engine, we know what we can do. However, in this there is still room for improvement. So from NASA, JAXA to ISRO to ESA to Roscosmonaut, everybody, every Tom, Dick and Harry dealing with space is working on this. Because if this works out, if they finally figured out how to manufacture it, how to use it in space, because of course in lab tested is already worked out, but in space when we are talking about, it's completely different volume. So that is why NASA is doing the demonstration mission, JAXA is doing demonstration, they have already done it. So if this works out, it can change the whole landscape. So we will go from having, let's say, docking systems that are docked to International Space Station for 6 months to a year, or maybe even 25 years. Let's say that means you can literally have a escape craft that is just put there and you don't have to worry about it. You don't have to cycle this spacecraft. Hey, it's a reaching 6 month expiry period, so fuel will start to corrode the tank. That won't happen. And if you can freeze it properly, so that also gives you much more peace of mind that it won't slosh around and change the center of gravity. So there are a lot of people, lot of money being poured into this. So in next 2 to 3 years, we'll have a lot of interesting results. So this was my presentation on green propellants. I hope you liked it, learn from it. In that case, please click the like button. If you didn't like it, don't worry about it. You can press dislike. I would urge you to press it twice to show me your extra disappointment. And please leave a comment because I reply to all of them. And check out my other videos. There are like 200 of them. And subscribe, press the bell icon if you're free. And as always, thanks for watching.